So next, let's talk about designing the AP and antenna deployment model for the best location results. So some guidelines for placing your APs. In order to make any given point on a map location ready, these are the requirements. It should be surrounded by at least 4 APs with 1 or more APs in each quadrant. So if you think of 4 quadrants, we need at least 1 AP in each of those 4 areas surrounding the client. In 3 out of 4 of those quadrants, we need to have an AP hearing the client at least a neg 75 dBm or louder signal level, ideally neg 72 dBm or louder. The ramifications of these requirements typically mean their APs are going to be spaced out somewhere between 50 to 70 feet apart, or in meters that would be 15 to 20 meters if they throw meters at you. APs should not be placed higher than 20 feet off the ground. Any higher than that, it becomes too hard to differentiate the signals based off a distance, because you're increasing the distance so much just from that vertical span that it has to go. And also, if you do location, only use Cisco antennas. So if you have an AP that uses external antennas, use Cisco antennas, because the location calculations have to know the radiation pattern of the antenna to do its calculations. So obviously the Cisco systems know the Cisco antennas. If you try to use a third-party antenna, it doesn't know the specific radiation pattern of those antennas, so it can't do the best location calculations that it could when compared to using Cisco antennas. So the calculation readings for location, when you have 4 or more APs that hear a client at neg 75 or louder, it's going to take all measurements at the neg 75 or louder. So as it does all the calculations, it takes into consideration all readings at neg 75 or louder, assuming you have 4 or more APs contributing at that signal level or better. Now, if you don't have at least 4 APs that can hear the client at neg 75, it shifts over to a little bit different method. So when you have three or fewer APs that hear it at neg 75 or louder, all measurements above neg 75 or louder are taken into consideration. So there's those 1 to 3 readings that are at neg 75 or louder. And then it takes the next 4 loudest measurements below neg 75. So you can have a lot more measurements coming into play when you get into something like this. So that's the method it uses in terms of how many measurements we use to consider for location. Either 4 or more at neg 75, it uses all of them above that, or 3 or fewer, it uses everything above neg 75, and then the next 4 loudest below that. Now, if you run into a multi-floor building, sometimes it can be a little hard to decide, okay, is the client on floor 2 or floor 1, because both floors might have APs that can actually hear the client. So how does it figure out which floor to place it on? So the first rule is if an AP hears a client at a neg 65 or better, it's going to assume the client is on that floor. Now, if you have APs across multiple floors that hear that client at neg 65 or better, now it uses what's referred to as a weighted metrics algorithm to essentially it has to guess as to which floor it's on. So what it does is it takes all the readings for the APs on a given floor, puts that into a calculation, and spits out a result. Whichever floor gets the highest result, that's where it places the AP. So the way that it does the metrics is that the metric of the floor is the average of each RSSI reading plus 90. So the way the math would look, so let's say on floor 1, we have a neg 60, and a neg 75. Floor 2, we have another neg 60, neg 70, and a neg 80. So calculation would be for floor 1, we have to do neg 60 plus 90 plus neg 75 plus 90, and then it's the average of that. So the number should be, we got 30 and 15, 45 divided by 2, 22.5. Hopefully I did the math right there. So floor 2, let's just shortcut this, so it's going to be the average of, so we have neg 60 plus 90 is 30, neg 70 plus 90 is 20, and neg 80 plus 90 is 10. If we add all this up, we have, what do we got, 60 over 3 equals 20. This one's higher, places it on floor 1. So that's how it does the math for that. All right, so a note on some other specific things here. Distributed antenna systems, or you might see it referred to as DAS. So flat out, Cisco does not recommend or support these for location. So you would never want to use this in a deployment where location calculations were important. One thing that has going against it is that it uses third-party antennas. Cisco doesn't actually create DAS antennas, at least as of today's recording. So one, we're using third-party antennas, which Cisco doesn't recommend for location. Two, the connotation of a DAS is that we have multiple antennas going back to one AP. So what it would kind of look like in a deployment would be we have our AP here, and then on one of the antennas of the AP would go out, and all of a sudden this would be a bunch of antennas all feeding back to one radio on an AP. So when the AP receives a signal on its radio, it says it sees a client, say the client's here, so maybe it's coming in this antenna over there, but how does the AP know that it's on that antenna? There's no intelligence behind it. So it could be coming, if it sees a neg 50 dBm, it could be a neg 50 dBm on any one of these antennas. So how do you place the AP on a map to know, where the location is being calculated? It really doesn't work. So for this reason, do not use DAS or distributed antenna systems with Cisco location. You're not going to get good results, and it's not supported. So location in outdoor environments. This is typically tough for Cisco. If you tried to use just the normal RF fingerprinting method, it kind of falls apart for a number of different reasons that you run into in outdoor areas. One, APs are typically spaced much farther apart outdoors than they are indoors. You're definitely beyond that 50 to 70 feet recommendation. You're probably getting into the couple hundreds of feet split out between APs. You're also probably having your APs higher than 20 feet. Usually they're closer to 25, 30 feet maybe up in the air. One, so they can get above obstacles and reach out since they have to go out so far. So you're violating that one. And I guess outdoor environments will interact with RF differently than they will indoors. So a lot of strikes against it in terms of using the normal RF fingerprinting method. So if you want to do location outdoors with Cisco, your real method is the TDOA. So you have those AP receivers that they have all their clocks synchronized, so they can do the calculations based off of that. And Cisco does support doing location off of TDOA receivers. So another difficult time you can run into with location, kind of like outdoors is a little bit difficult, is when you have dense AP deployments. So oftentimes the AP designs that you come out with when you have to do a data voice type of survey doesn't provide optimal location coverage. It might get you mostly there, but there's gaps in terms of having a location ready area everywhere in your map. So usually where it falls short is on the edges of the building or the corners of the building. So if you think about just a real generic rectangular building here, we want to get any area on the building surrounded by those 4 APs, hearing at neg 75 or better. So it typically means that we want our APs in the corners. Depending on how big the building is, we might need to fill in on the edges there, and then somewhere in the middle we need to have it so we get that 50 to 70 foot spacing, in that ballpark from a maximum standpoint. So an ideal location deployment might look like that. But depending on your actual design for your data and voice networks, some of these APs might not be there. maybe these guys aren't there for one reason or another. Or more typically, it's going to look like something like this. A little bit narrow design, and you get kind of this little sawtooth pattern going on. So that would give you everything you need for data voice. But if you think of the location ready as based off of a perimeter of your access points, you'll get good location in the middle here, but on the corners, not good because these guys are not surrounded by APs. Well, you could say, okay, then just throw some APs in the corner. What you run into with that, though, is if I just put in a couple more local mode or HREAP mode APs in the corners, now, since these radios are active, they might start powering down the surrounding APs, and that might start causing coverage holes because I assume that these APs are at a certain power level or higher. So what you can do is rather than putting these APs in the corners as local mode or HREAP mode, you can put them into monitor mode so they're not contributing to the RF environment in terms of broadcasting the signals. The neighboring APs won't be getting neighbor messages from them, so they won't possibly power themselves down. So we get the coverage that we anticipated based off of our survey, but we're also enhancing our location because we're adding these extra APs, and now my perimeter goes all the way around the outside and everything's happy. So monitor modes are usually the solution to shoring up weaknesses in your standard data or voice AP deployment design. Now just make sure that as you're doing your standard data voice AP design, you're trying to do it with location in mind. So try to, as much as you can, get the APs in corners, get them going around some of the edges of the buildings, and then use monitor mode APs to fill in the gaps where needed. Another further enhancement that you can use with these monitor mode APs is a mode called Tracking Optimized Monitor Mode, or TOMM. This is only applicable in the 2.4 gigahertz spectrum. What it does is it allows you to specify a subset of channels for these specific monitor mode APs to scan. And what you would do is you configure those to scan on the channels where your clients are actually located. By default, monitor mode AP will scan every channel. So that means it's spending time on channel 1, 2, 3, 4, and so on. But if I only have clients on channels 1, 6, and 11, it's spending, what, a third, 2/3 of its time or something like that on channels where I don't even have clients. So it will not grab client information while it's on these other channels that the clients are not actually on. So you can put it in Tracking Optimized Monitor mode, and it will always be on a channel where the clients could possibly be. That just means that you get more data to calculate location off of, rather than missing a lot of that information. Again, only on monitor mode APs, only in the 2.4 network. We can select up to 4 channels. So in the US it would be 1, 6, 11, but in Europe they actually have 4 valid channels they can do. In Europe it's usually 1, 5, 9, and 13 would be their non-overlapping channels. Kind of coming back to one of the things I had mentioned before, floors with multiple types of areas. This is another difficult place that you can run into in terms of doing location. So with WCS, the RF fingerprinting, the path loss model is applied to the entire floor. If we have areas that have significantly different loss values, really open area, really densely obstacled area, it won't be as accurate. So the 2 options for that, either use the path loss model for the area that you care about location. If you don't care about location over here, you only care about it on this side, then use the path loss model that most matches this side over here. If you need accurate location in both areas, split the single floor into 2 logical subfloors, and then have floor A, 1A over here, floor 1B over here. They can have their own path loss models, and then we get accurate location in both spots, but it's a little bit of a hassle. You do have to logically separate these floors out into 2 different floors. And then location at small sites can also be difficult too, mostly because in a small site you might only have 1 or 2 APs. Hard to get 4 surrounding APs when you don't have 4 APs. So if you have a small site and you absolutely have to get location in there, you have to install at least 4 APs. That might be way overkill in terms of the RF needs of the area. So you might just deploy your 1 or 2 local mode or HREAP mode APs that you need for the coverage, and then put in some monitor mode APs to supplement that, like we had talked about with the dense deployments. Or you might just turn them all into local mode or all into HREAP mode. It just depends on what the ramifications are going to be in terms of AP power levels with that. So one or the other, you just need to get enough APs so that you can surround all areas, with the 4 or more APs.